Picture your cardiovascular system as this sprawling, bustling metropolis. Now imagine a highly efficient logistics network running through that city, right? You've got billions of microscopic delivery trucks rushing through the streets every single second. Their cargo is oxygen. It's literally the ultimate fuel, keeping every building, every factory, every single cell in that city alive and functioning. But what happens if those trucks suddenly just stop arriving? Today, we are looking at the ultimate biological supply chain crisis. Welcome to this explainer on decoding anemia.
So what actually happens to the human body when its ultimate oxygen delivery system is running on empty? Look, this isn't just a simple illness. We are talking about a systemic crisis. It's a full-blown medical detective story where the stakes honestly couldn't be higher. Tissues start to starve, organs are struggling to keep up, and the body starts sending out these desperate SOS signals. Our job today is to learn exactly how to read those signals and catch the culprit.
To get there, here's our clinical roadmap for today's explainer. We're going to cover the science of anemia, check out the high-yield clinical signs, differentiate the etiologies, decode the diagnostic workup, and finally, nail down that final diagnosis.
Let's dive right into Section 1, the science of anemia, defining the core problem.
Okay, so the absolute crucial point is right here in this definition. Anemia is a state where the level of hemoglobin in the blood drops below the normal range. Pay close attention to those threshold numbers. For biological males, we're talking 13 to 18 grams per deciliter. For biological females, it's 11.5 to 16.5 grams per deciliter. Now, hemoglobin is that specific protein molecule in your red blood cells that actually carries the oxygen. So when this number drops below the threshold, it means your primary oxygen delivery mechanism is actively failing. The trucks are officially off the road. Once we actually confirm that hemoglobin drop, our investigation has to shift immediately to a targeted history, because this is where we find our first massive clues. We're looking for things like acute or chronic blood loss, GI bleeding, hematemesis, melena. Or maybe we find neurological symptoms like tingling and numbness. That takes our whole investigation in a completely different direction. Literally every question we ask narrows down our suspect list.
Which brings us to Section 2, high-yield clinical signs, the physical clues.
A really thorough physical exam acts as our initial forensic sweep. The human body basically becomes a canvas here, and the disease leaves very specific, observable fingerprints behind that reveal all sorts of hidden clues.
And these physical clues, they're highly specific to systemic failures. Take frontal and parietal bossing, for example. That prominent, bulging forehead is a massive red flag for hemolytic anemia, right? Because the bone marrow is literally expanding to desperately try and replace destroyed red blood cells. Move down to the hands. Koilonychia, or spoon-shaped nails, points a direct finger at iron deficiency. Check the mouth next. Angular stomatitis and that smooth, raw tongue we call glossitis. That tells us we might be dealing with either a B12 or an iron deficiency. And what about a general finding of jaundice? Well, that yellowing points us right back to the rapid red blood cell breakdown of hemolytic anemia.
Let's move to Section 3, differentiating the etiologies, our suspect lineup.
Let's go ahead and contrast our first two major suspects. Suspect 1 is iron deficiency. This is the most common culprit by far, and it's often tied to a history of GI bleeds, peptic ulcer disease, or even chronic NSAID use. The body simply doesn't have the raw building blocks to make the trucks. Then we have suspect 2, which is vitamin B12 deficiency or malabsorption. This suspect leaves a totally different calling card. It brings these distinct neurological clues like tingling, sensory numbness, and even visual disturbances. So it's the exact same crisis of low hemoglobin, but a completely different underlying mechanism.
And this slide brilliantly illustrates the other side of our suspect lineup. Aplastic anemia is characterized by total bone marrow failure. It's basically an empty factory where all blood cell lines are low, and that's often triggered by things like cytotoxic drugs, radiation, or a viral history. Contrast that with hemolytic anemia. Here, the factory is actually working fine, but there is a destructive battlefield out in the bloodstream. Red blood cells are experiencing accelerated breakdown, and that's usually due to inherited membrane defects, autoimmune issues, or enzyme deficiencies.
All right, Section 4, decoding the diagnostic workup, the forensics.
So, to pinpoint the exact etiology, we have to rely on essential, highly specific lab panels. If we suspect our battlefield scenario, hemolytic anemia that is, there are 3 specific lab tests that will conclusively crack this case for us.
Let's decode exactly how these labs build an airtight forensic case.
First, the reticulocyte count, which measures immature red blood cells. If those are increased, it tells us the bone marrow factory is working overtime, frantically pumping out new trucks to compensate for the ones getting destroyed out there. Next up, serum LVH. When red blood cells actively break open in the bloodstream, they spill LDH. So, an elevated LDH proves there's active destruction happening. Finally, indirect bilirubin. When hemoglobin gets broken down, it turns into unconjugated or indirect bilirubin. An elevation here, usually keeping it less than 4 milligrams per deciliter, well, that confirms excess hemoglobin breakdown. Put these 3 labs together, and you've got a smoking gun for hemolysis.
But what if it's not hemolysis? Let's look at another brilliant forensic tool, the MCV, or mean corpuscular volume. This simply measures the physical size of the red blood cells, and it completely splits our suspect list in half. If the lab shows microcytic cells, meaning the MCV is low, under 80 femtoliters, the forensics point straight to iron deficiency. The cells are small and pale. But if the lab shows macrocytic cells, a high MCV over 100 femtoliters, it indicts a B12 or folate deficiency. The cells are large and improperly formed. It's wild how just measuring the physical size of the delivery truck tells us exactly what went wrong back in the factory.
Now, what if the factory is just shut down completely? If our lab work shows few to no reticulocytes alongside a drop in all blood cell lines, a condition we call pancytopenia, well, the forensics strictly point to aplastic anemia. The bone marrow has just failed. There are no new trucks, no new white blood cells, no new platelets. The entire logistics network is completely offline.
And that brings us to Section 5, the final diagnosis, closing the case. By bridging the macroscopic physical clues we found on the body, stuff like the spoon-shaped nails or the jaundice, with the microscopic forensic lab data, like MCV size and reticulocyte counts, we can decisively solve this oxygen crisis and target the exact right treatment to save the system. And I really want to leave you with this final thought to ponder today. We've just seen how a drop in one single protein can essentially bring the entire human city to its knees. So if our circulatory logistics are this fragile, what other invisible networks inside us are just one tiny disruption away from a complete systemic crisis? The human body is an absolute marvel of engineering, but it's a very delicate balance. Keep observing, keep questioning, and definitely keep exploring those microscopic mysteries.